Hi guys, Ross here, and I'm going to go over some of the instrumentation that we're going to use aboard the Beam Me Up vessel to conduct these bridge inspections. First of all, integral to our operations on the boat is the IMU. We use a Teledyne Orion INS system, and it uses three separate ring lasers and accelerometers to measure heading resolutions as accurate as a hundredth of a degree, as well as roll and pitch measurements to as well a hundredth of a degree. And the heave corrections are directly obtained by RTK, allowing for heave measurements as accurate as 5 centimeters. This unit has also been approved by the International Maritime Organization, so we definitely depend on its reliability and accuracies. Now, getting into the majority of our operations, we will be using a multi-beam echo sounder. We use a Teledyne Reason CBAT T50R dual frequency multi-beam transducer. Like you saw in the model of our vessel, the CBAT will be attached to a side mount on the port side of the vessel and then lowered into the water. Now, the height of this pole mount can be adjusted from anywhere between 4 to 10 feet, depending on the conditions necessary. The Teledyne Reason CBAT uses 512 beams spread out in multiple different beam forms. For our purposes, we will mostly be using an equidistant beam form, which creates a data density across the swath that leads to greater efficiency by minimizing overlaps, thereby reducing the number of lines required to survey any given area. That being said, there are a lot of bridges that need our help, as we've stated, and so we need to figure out ways to do this as expeditiously as possible. Furthermore, the sensor head can actually be tilted and rotated, so if we are in any areas where we may not be able to get to with our vessel, we can direct our sonar measurements to that area. The CBAT allows us to collect the swath width of 150 degrees when it's set at that equidistant setting, and with that, we can reach a depth resolution of 6 millimeters when using a frequency of 400 kilohertz at 350 meters and 150 kilohertz at 850 meters. We will adjust the frequencies depending on the specifics of the job site, depending on the quality of the bottom, the quality of the water, and the depth of the water. Now I'm going to move on to a picture of what the sonar data looks like when it's collected. As you can see here, this data is very, very dense, allowing us to see very fine fractures or other problems with the ground where these bridges are built on. Now, in accordance with our multi-beam, we also use a single beam. The single beam, again, is hull mounted, and we usually utilize it for quality control primarily. This is just a internal check for us to make sure that the data that we're collecting is as best quality. Again, we will be moving as quick as possible to make sure as many bridges can get done in the allotted amount of time. Now, after the transducer has been calibrated for speed of sound, draft, and indexed using the bar checks and velocimeter that Tim touched on earlier, it's going to provide us other benefits as well. Using a narrow beam at low frequencies, we can focus on areas with hard bottoms, and that's going to allow us to uncover ground stability issues that we may not have been able to notice just by regular scan. And in addition, we're also going to be able to analyze the type and amount of sediment and vegetation in the area, which is important if we're to understand what the cause of some of these bridge erosion and scour situations is. Furthermore, we're going to be using a Carlson Merlin LiDAR scanner, which is going to be affixed to the hull of our ship. This scanner has a 360-degree view, which can emit 36,000 points per second at a distance of 250 meters will give us a 1 centimeter accuracy. 250 meters we felt is acceptable for this application, being that we will have the ability to get close to these bridges as we need to. Of course, these LiDAR measurements are corrected for using the GNSS systems and as well as the IMU. Now, when we do take these LiDAR measurements, we have the ability to synchronize them with the multi-beam data that we are collecting. The data is put through a onboard software that we'll touch on later, but it allows us to see both the undersides of bridges, the sides of bridges, as well as the underwater parts of the bridge to give a full detailed analysis. And we are able to actually view this type of model in real time using the onboard software. That way, if we see any major deficiencies, we can address them immediately. As well, we also have a 3D submersible scanner. Now, a lot of times when we're doing our multi-beam scans, we're not able to accurately get into smaller areas. Also, we might see an area where we have a little bit more concern and are unable to get a closer look at it. And if that's the case, we're going to employ a 3D SL3 submersible scanner. Now, this scanner has many different mounting options. We chose a more cheaper option to save costs to the client by mounting it on a tripod. This tripod is then leveled and measurements can begin. And underwater we can achieve 2 millimeter accuracy, and we can achieve depths of 3,000 meters if we do decide to put it on an ROV or AUV system. As you can see on the picture to the right, we're able to very accurately discriminate between what types of scour we are finding and whether they need to be addressed immediately or not.